Welcome to my talk on sampling distributed schedulers for resilient space communication. I am Arndt Hartmans, and what I'm presenting is the result of joint work with Pedro D'Argenio and Juan Freire. I would like to start by quoting reviewer number 2, who commented that our paper has the flavor of a case study driven exercise. I think this is a very accurate observation because our research started out from the problem of computing optimal routes through satellite constellations where the contacts between the satellites are uncertain and may or may not work for communication. This really fits with the model of Markov decision processes very well, so one may want to use probabilistic model checking. However, there is the known problem that probabilistic model checkers compute strategies that we cannot implement on satellites due to using global information. So we then contribute a way to make statistical model checking compute actual implementable strategies using lightweight scheduler sampling and building on a new definition of distributed schedulers. So we provide theory on the one hand and a working tool chain that we exercise on an example as well. Let me now start with a few more details on our application scenario. As mentioned, we are looking at routing data through satellite constellations. And in the picture here, you see the Earth and various ground terminals. The domes are the communication ranges of these ground terminals, and there's a particular ground station connected to the internet in the southern hemisphere in Cordoba, Argentina. You could think about these ground stations as, for example, measurement nodes that are deployed in remote locations and that occasionally want to send their data back to the ground station and to the internet. We also have satellites in low Earth orbit that are circling around the Earth and that may cross the communication ranges of the ground stations and that may also meet closely enough with other satellites such that they can communicate with them. And one may want to do real-time communication through these satellites. This is what these companies that nowadays launch lots of satellites to provide internet to remote locations do. But they need large constellations because they need simultaneous chains of links in order to establish internet access. As I mentioned, we are rather looking at scenarios like this data collection from sensors where there is not a real-time requirement. It is okay to occasionally get the data from ground onto a satellite, store it on the satellite, carry it forward, maybe communicate it to a different satellite that then on the next orbit passes close by the ground station and hands the data off. Definitely not real time, but it allows us to use much sparser constellations to perform the communication if we compute a good plan of how to route our data through which satellites, such that the data eventually arrives at the destination and doesn't just orbit the Earth for a very long time stored in the memory of some satellite. Now, the communication windows, when a satellite can receive or send data from or to a ground station or another satellites, they are known in advance, at least for a certain time horizon, because you know up to a certain accuracy the orbital parameters of your satellites, you know the communication range of their antennas, so you can come up with a contact plan. And here's a very abstract representation that we use of a contact plan, where we have time slots T1 to T5 and 4 nodes N1 to N4, satellites or ground stations. A real contact plan, of course, has real time windows of different durations. And we use this discrete view here to make studying this feasible from a theoretical viewpoint. Now, given such a contact plan, DTN routing algorithms can pre-compute routing strategies for the next day or the next week or so. However, DTNs are subject to a number of uncertainties. So you may not exactly know what the orbits are, but only up to a certain precision. The satellites may not hold the orbits fully accurately all the time. They are very cheap satellites usually. I mentioned CubeSats at some point. And so they may just have faults. They are usually not very much shielded for radiation, for example. So messages can simply get lost when we try to communicate. And again, taking a very abstract view, we thus have uncertain contact plans where every link can succeed or fail to transmit a message with a certain probability. And if you now want to do routing through these, you have to account for the failures. And you can do so by copying your messages, trying to maximize your probabilities of success. However, you are quite constrained in resources on these simple satellites, so we don't want to just flood the whole network with lots of copies of the message. In uncertain contact plans, like the one shown on this slide, we thus have strategic choices to make, and we have random behavior. Together, this fits exactly with the model of Markov decision processes, or MDP, and then we can turn a contact plan into an MDP and use a probabilistic model checker to find the routing strategy that gives us the highest probability of success. We also refer to strategies as schedulers, because that is the classic word used in probabilistic model checking. In other areas, they may also be called policies or adversaries. Now, what is the best scheduler for node N1 if we want to get our message to N4 in the end? And let's limit to 2 copies here. So obviously in the first slot, we will send 1 copy to node N2. And we assume that you can send as many copies as you like during one slot. And it doesn't make sense to send more than 1 copy here. Now, the real question is, what do we do in slot T3? Should we send to node N3 or not? And this depends on whether N3 did get the message from N1, the first copy. If it did, then we should not send it another copy. It already has one, it would be wasted. So we only send to N3 in slot T3 if it did not get a copy. And if that is not the case, if it did get the copy, then we save our own copy for slot T5 to try sending it to T3 with a low probability, but still directly. Now there's a little problem with this strategy, and it's this condition here, because satellite N1 cannot know the state of the memory of satellite N3. In a scenario with acknowledgement-based communication, it could know whether the first copy arrived at N2, but definitely not at N3, which it hasn't talked to so far. The problem here is that the probabilistic model checker computes a strategy that uses global information, and that doesn't work in this setting. The problem that probabilistic model checkers need global information for their optimal strategies is known and has received some attention in research, mostly in the 2000s. So the idea then was to use distributed schedulers instead, which are limited in the information they can use. Conceptually, a distributed scheduler can be partitioned into 1 scheduler per parallel component, in our case per satellite, and it would have to make its decisions based on some notion of local state only. In addition, you need an interleaving scheduler in certain scenarios, which decides which component goes first in case 2 of them can make perform an action at the same time point. For the satellites, this is not so relevant, but this could be relevant if things run on the same CPU. Think about parallel algorithms, mutual exclusion. It is often very important which thread gets to set a variable first. Now, first, this problem of distributed schedulers was looked at from a more theoretical perspective. The first algorithms were for partial information settings, but those are really different from distributed scheduling. You may have heard of partially observable MDP, POMDP, but that is a different and in a certain sense a bit simpler setting because it has only one partial information view, whereas we have multiple agents that have different restrictions on what they can see. Now, the main result on distributed schedulers was a very sad one in the mid-2000s. The things we want to do are undecidable. And even if we limit ourselves to memoryless schedulers, which cannot be as good as non-memoryless ones, it's still NP hard to find the optimal one. Later on, this problem of interleaving schedulers was looked into because it turns out that they can disclose information from one component to the other in unintended ways, which makes it problematic to study security protocols, for example. And this was solved by defining strongly distributed schedulers. Then tools were also built, but they turned out to really suffer from the exponential blow-up of these NP-hard problems, and no probabilistic model checker of today implements distributed schedulers. However, we are doing a case study driven exercise, so we would like to get a practical result. And here's what we do instead of using probabilistic model checking. First, we define simple distributed schedulers that remove most of the complications of the strongly or non-strongly distributed ones. First of all, they are memoryless, because that is what we can realistically implement. We don't have the infinite memory we need for non-memoryless schedulers, and we also have resource constrained nodes, so we do not want too much finite memory. So we go for memoryless, and we also define them for the setting of Markov decision process models with parallel composition and communication through global variables, because that is what modern modeling languages and formats like the Jani format give us, whereas the literature usually used communication through synchronization, handshaking only, which is cumbersome to build large models with. Now, in addition to this notion, we give a definition of what is a model that is good for distributed scheduling. And this you can check on the state space, and you can also ensure by construction. And if you have such a model, it means that the interleaving schedulers have no effect on the resulting probabilities and strategies. So these are kind of the good models that we want. And then we use statistical model checking with lightweight scheduler sampling to perform an effective analysis, which I will explain on the next slide. So we don't use probabilistic model checking, but instead choose to use statistical model checking, SMC, which in essence is Monte Carlo simulation on formal models. It has the limitation that it cannot properly deal with MDP, because Monte Carlo simulation is about estimation, not about optimizing choices. In order to make that work, we use the lightweight scheduler sampling approach by Setworks and others, where M schedulers are sampled at random, and then for each of them we independently do a statistical model checking analysis. The key insight of this LSS approach is how to represent a scheduler very efficiently in memory by a single integer through clever use of hashing and pseudo-random number generators. The nice thing about this approach is that it is very easy to adapt it to any setting with partial information, because you simply limit the information that you put into those hash functions. And then we can adapt it to work for our simple distributed schedulers. This is the pseudocode of the algorithm, which we explain in more detail in the paper. One caveat that I should mention, that should be clear if you think through how this approach works, is that it need not find the optimal scheduler. It just chooses m schedulers at random, and it could be that they are all far from optimal. So the result that we get is always a lower bound on the maximum probability, and it depends on how rare the optimal schedulers are when sampling randomly, how good our probabilities are in the end. We then build a tool chain to deal with space delay tolerant networks from the specification of the orbits all the way down to a scheduler identifier. Now, first we have a Python tool built by Juan to take a contact plan in a standard format and convert it into a modest model. Modest is a formal modeling language for stochastic timed systems and can represent MDP, a bit similar to a programming language. So here's an example of a modeling of a modest model for one of our nodes here. We generate these automatically, and in particular in a way such that they are good for distributed scheduling by construction. Now, we then implemented the new variant of scheduler sampling for simple distributed schedulers in the MODES simulator, which is part of the modest toolset, so that in the end we get the probability of the best scheduler that it could find. We have exercised this tool chain first on the example simple contact plan that I've used a few times in this talk, and then on a satellite constellation of 12 satellites and 12 ground nodes, of which you've seen the pictures a few times already. Here are the results that we get. So first, I'm just showing the probabilities that we can compute for the example contact plan with probabilistic model checking. That means using global information. We look at two scenarios, one with fully unreliable communication, where you send a message and you can't know whether it arrived, and one with acknowledgements where if it arrived, you will know because you get an acknowledgement. Now, for the first setting here, we can by hand also calculate the probability of the best distributed scheduler, which we see is a bit lower than the one that the best global information scheduler can obtain. Now let's put our tool chain onto this problem and use 1,000 schedulers that we sample, 1,000 random schedulers. Then if we sample among classic global information schedulers, these are the values we get. Not quite exactly the best probability, but very close. And what I'm showing here is in brackets the best result over 3 repetitions, so over 3,000 schedulers. And the larger numbers on the left are the average of these 3 runs. Now, for distributed schedulers, we get the result 0.46, which means that we are within the statistical error of the optimal result in the unreliable case. If we now go to more schedulers, so sampling 10 or 100,000, we see that the values improve, and very quickly we find near optimal schedulers for this small example. Interestingly, in the case with acknowledgements, the distributed schedulers obtain the same probability as the global information ones, which is due to an interesting collaboration via acknowledgements that we explain in the paper. For the Walker case study, these are the values we get. So here we only know the true optima for the global information schedulers. And we see that if we only sample 1000, then we are very far from the optimal values. In the distributed case, we even get higher probabilities of success among the 1000 schedulers. And this is because distributed schedulers have fewer choices, so there are fewer of them, which also intuitively makes it more likely to hit a good one if we sample randomly. The picture continues as we go to more schedulers, the values improve, but still we get better results from the distributed schedulers than from the global ones, because we have this trade-off of having more power on the one hand in the global schedulers, but also having fewer schedulers, so optimal or near optimal ones are not as rare as in the more powerful set. To summarize my talk, we wanted to solve the problem of routing in delay-tolerant networks with uncertain contact plans. And we were happy with a practical solution to this. So the problem is that we cannot use probabilistic model checking. So instead, we propose a variant of statistical model checking with adapted lightweight scheduler sampling. And we provide an entire tool chain to work this method. Thank you for listening. And at this point, I would be happy to answer questions.